Okay, let's look at some differential equations today. So we're going to start by looking at a pretty basic differential equation. The differential equations we're looking at in this class are in general, ordinary differential equations, or ODEs. Okay. There's also a field called PDEs, partial differential equations. And we don't have to worry about the distinction here, but you'll hear people talk about ODEs and PDEs. That's ordinary differential equation, partial differential equation. Sometimes you'll hear Diff EQs, because differential equations is too long to say, I guess. Anyway, here we go. Let's talk about it. So we're going to use our knowledge of integration basically to go backwards from a derivative to find the original function. We've done this before. We're adding in one last little thing, and that is the notion of an initial condition. Okay, so we say the derivative of y with respect to x is equal to x plus e to the x. Find y. Well, if we know that dy dx, which could be written as y prime, is equal to x plus e to the x, then if I want to find y, then I should simply be able to integrate. Y should be equal to the integral of x plus e to the x dx. Okay, well we know how to do that. That's simply going to be x squared over 2 plus e to the x plus an arbitrary constant c. The only difference now, I'm going to rewrite this just to rewrite it. The only real difference now is that now I'm saying, hey, guess what? In the original function, if I plug in a 0 for x, I get 1 for y. Because notice this is the solution to many, many, many different equations, right? So this could be the solution to many different differential equations. Likewise, if I didn't tell you initial conditions, the solution to this could be many different equations. And in particular, it could be any equation of the form x squared over 2 plus e to the x plus a number. So we have to figure out which particular number do we want as a solution. Well, we want the one that when I substitute an x in, I get 1. So let's do it. Let's substitute an x in. If I plug in x equals 0, I get 0 plus e to the 0 plus c, and we know that should be equal to 1. Okay. All right. Well, if that's the case, e to the 0 is 1 plus c equals 1. So therefore, c equals 0. And the correct solution to this equation, to this differential equation, is x squared over 2 plus e to the x, because this is the equation where when I take its derivative, I get x plus e to the x, and when I plug in 0 in for x, I get the number 1. So here's my solution. Okay. All right, so what do? We start out with a function. The function was a derivative in terms of x. That's important here. And the general solution here was given by, if I take the integral of the right-hand side, I'm going to get the antiderivative plus c, and then we must use an initial condition to find the constant c, to find the particular solution. So this is a general solution. When you have the plus c, you get a particular solution when you solve for that c. All right, so here's another example. This time we're using a second derivative. So we're just going to have to do the process twice. Okay, so if we want to find y, well, we are at y prime, y double prime. So if we want to find y prime, I've got to take the integral of this, 6x minus 1 over x squared dx. Let's do the work. We're going to get 6x squared over 2 minus, this is x to the negative 2. So I'm going to get negative 1 over x to the negative 1 plus c. Let's go ahead and simplify that. 3x squared plus 1 over x plus c. Okay, so that's y prime. But now remember, we're looking for y double, or originally y. We started with y prime, y double prime. We ended up with y prime. We have plus c. So we need to use the initial condition that tells us that when I plug a 1 into y prime, I get 12. So here, let's do it. I get 12 when I plug 1 in. So this is going to be 12 equals 4 plus c, so c equals 8. Okay, that means that y prime is equal to 3x squared plus 1 over x plus 8. Very good. But now I need to use this again because I want to find not y double prime, not y prime, but y. So I'm going to have to use this process again. To find y, I'm going to take the integral, again, of 3x squared plus 1 over x plus 8 dx. Okay, so I'm going to get x cubed plus ln of the absolute value of x plus 8x plus c. Again, this is a general solution because I have a plus c. I don't have plus an actual number. I want to find an actual solution. The actual solution is given for when I plug in x equals 1 in, I get 8. These are initial conditions here. So I'm going to use this second initial condition for y. So I should get 8 if I plug in a 1. 1 cubed, ln of 1, 8 times 1, plus c. Okay, so I get 8, 1, ln of 1 is 0, it's 8, plus c, so c equals negative 1. That means, pardon my crazy up here, that means that y equals x cubed plus ln of the absolute value of x plus 8x minus 1. So, this is the equation where when I plug in a 1, I get 8. Okay. And when I plug in a 1, I get 8. When I take the first derivative, okay, and I plug in a 1, I get 12. So that checks off, that checks off. And when I take its second derivative, this is the equation I end up with. That's what we're looking for. All right. So now let's look at something very similar. Okay, it's an extension of what we just did, and it's called separable differential equations. Okay, so here's what we have. I have something xy prime equals y squared times x plus 1. Now notice the problem here is that I have x and y's mixed together, okay, and y prime is not isolated already. So in a case with separable differential equations, I think it's more helpful in general to rewrite the equation as x dy dx and then y squared x plus 1. So with separable differential equations, it's not as easy as having dy dx solved for and x is on the right. So what we've looked up to this point is this with only x's over here. Now we have a situation where even if I pull the x over here, I still have a y squared on the right. So here's what I'm going to do. I am going to pull the x over here, but I'm going to do something else as well. I'm going to separate the dy dx. So I'm going to have x dx equals y squared x plus 1 dy. Now look at this. I've separated dy dx as if it were a fraction. It's almost like multiplying, oh, pardon me. It's almost like multiplying on both sides. I have x dy, pardon me, and on the right I should have dx. So if I multiply dx on both sides, that's what I did here. I said dx. Dx is almost as if these cancel, but we don't cancel them. We simply say by the chain rule they undo each other. And now I have x dy equals y squared x plus 1 dx. So what I want to do here is I want to get all the x's on this side with the dx, and I want to get all the y's on this side with the dy. So I'm going to multiply and divide to get that done. Alright, I'm going to multiply the x over here by dividing by x. I'm going to multiply the y over here. So I'm going to get dy over y squared. I'm going to get x plus 1 over x dx. Okay? Now look at this. Now I have 1 over y squared dy and x plus 1 over x dx. I can simply integrate these now. Okay? Alright, so what I have here, this is 1 over y squared, or y to the negative 2. So I'm going to get y to the negative 1 over negative 1 equals, and this is x over x plus 1 over x. So the antiderivative of, I'll rewrite that for you, 1 plus 1 over x dx. This one over here is y to the negative 2 dy. So what I'm doing here is I integrated this, and now I'm going to integrate this over here. The antiderivative of x is x, pardon me. The antiderivative of 1 over x is ln of x plus an arbitrary constant c. All right, so what I have here is I have negative 1 over y equals x plus ln of absolute value of x plus c. And remember, this is a general solution. Now, the issue with these separable differential equations, you're never guaranteed with problems like this that you can solve for y. You're never guaranteed it. In this case, we can simply by cross multiplying, and I end up with 1, or should I say negative 1 over x plus ln, the absolute value of x, it's L and an n, absolute value of x plus c equals y. So in this case, I can do it, but there's no guarantee when we're talking about problems where the derivative is mixed up inside of the equation, and when you have, in the case of y squared, when you have that kind of issue going on, you're never really guaranteed that it's going to work. In this case, it just so happens that it does work, okay? But you're never guaranteed that, okay? All right. So here's the concept. We separate dy dx as if it were a fraction with 1 on each side of the equation, a dx on one side and a dy on the other. We multiply so that the x's appear only with the dx term, and the y's appear only with the dy term. The only way we can do this is if we multiply and divide. Adding and subtracting them to one side or the other won't do anything for us. Then we integrate both sides, and finally we solve for c using initial conditions. A word of warning here. There's a whole field of calculus, as I mentioned before, differential equations, the entire course is just about these kinds of problems because you can't always do it. Okay, it's not always possible to do step 2. Now, any problem that I give you on homework is going to be possible. Don't worry about that. But just keep in mind that this is not a guarantee that you can always do this. That would make integrating very difficult. Okay, so I want to look at one more particular kind of differential equation, and that is an exponential function. An exponential function is an interesting beast. What it is and we've talked about exponentials before, you certainly have in pre-calculus. What it is the rate of change of the function with respect to time. So as the function changes with respect to time, it's proportional to the original amount. What does that mean? Okay, well that means that if I start with, let's say we have a function that's 3 to the x. How fast does that grow? Well, if you had, let's say you had an amount, let's say you started with 3. That's an easy one. Well, as you increase from x equal to 1 to x equal to 2, now you have 9. Okay. Now you increase again. Now you have 27. Every single time we're multiplying by a factor of 3. So from one value of t to the next value of t, we're increasing by a constant factor. That's what this is saying. The rate of change increases by a constant factor. So it's the derivative of an exponential function is increasing by a constant factor. That's what makes it exponential. This is another way to say that. An exponential function is one where the derivative increases by a constant factor. Okay, so how can we see that this is actually a exponential function? Well, here's how we do it. We can actually go ahead and use our notion of differential equations to solve for this. Okay, I can either use my separable or my regular, but I'm going to go ahead and separate. dp equals k p dt. I'm sorry, we actually need to be able to separate. Okay, now remember that k is just a constant. K is not a variable. It doesn't really matter which side it's on. We'll leave it over here, but we need the p on the left-hand side. So I'm going to divide both sides by p. And now I get that 1 over p dp is equal to k dt. Integrate both sides. What do we get? We get ln of the absolute value of p equals k t, because k is just a number, plus my arbitrary constant c. Now I haven't solved for p at this point, right? Now I need to solve for p, and I'm going to take e on both sides. And what do I end up with? I end up with p on the left, e to the kt plus c. But I can write e to the kt, this is addition, as e to the c. And what you'll end up seeing people write is the proportion, pardon me, the population, this is often a p for population, is equal to some number which e to the c, okay, e to the c times e to the k t. Now, you probably haven't seen this formula before. Instead, you'll see people, because if c is a constant, some arbitrary constant, then e to the c is some arbitrary factor. So we just call that b. Okay. This is the formula you've probably seen for exponential functions before, and we can derive it directly from this notion that all an exponential function is taking the amount that we had before and multiplying it by a constant number. That's what exponential means. So we can take that idea of what it means to be an exponential function and derive the equation for an exponential function, where again, p is the population at time t, okay, b is the initial amount, e is that crazy number, k is some number that stays the same, and in particular it's the number that we're increasing by every single time, and t is the time. Okay, so we have b and k are constants for a function, and t and p are variables. Okay, so that'll do it for today, and we're going to talk more about this in class. Thanks, guys.